So having taken a look at how the approach of attacking the representation of a physical problem using thermal circuitry, having taken a look at how that works, now what I wanted to do is to kind of mix it up a little bit. And I wanted to mix it up in two different ways. One, I wanted to take a look at the one kind of thermal resistance we haven't seen in practice yet. We've derived its expression, but we actually haven't handled like an example problem that deals with it, which is the cylindrical conductive thermal resistance. And what I also wanted to do was I wanted to throw a wrench in the mix and say, well, what happens if not all parts of the system, of the physical thing that I'm trying to understand, are governed by the assumptions that are required for thermal circuitry? Okay? Can the thermal circuit assumptions, can that framework of thought and analysis still work? And the answer is yes, it actually works quite well. So let's take a look at how we do it. Well, here's the physical system that I want to consider. Let's suppose that I have some kind of fuel rod, which is a solid object. It has a constant volumetric thermal energy generation rate, Q dot, inside of it, inside of this main cylinder. And it has some thermal conductivity, K1, and it has some radius R1, okay? This thing is surrounded by, say, cladding, right? And this cladding has an outer radius R2 and has a thermal conductivity K2. It doesn't have any thermal energy generation, right? So all of the thermal energy generation, the Q dot, is happening in here. But nevertheless, this is still a solid object with, some thermal conductivity K2 and some outer radius R2. And then we can say, okay, well, the temperature on this interface between the cladding and this fuel rod is T1, and then the temperature of the outer surface of the cladding is T2. And all of this is surrounded by, air or whatever, some kind of liquid, with some heat transfer coefficient H between the outer surface of the cladding and that liquid, and then the liquid is at some characteristic temperature T infinity. All right, so this is sort of the setup that we're trying to go for now. One question that we might ask ourselves is, can we model this with thermal circuitry assumptions? Two, does this even work? Right? Can we get meaningful information about, say, for example, what the temperature inside of this rod looks like, even though we've got this Q dot? Because let's take a look at the thermal assumptions, the thermal circuit assumptions again. Are all of the material properties constant? Well, they're just individual numbers, so sure, right? We're not expressing them as functions, so great. Is the system in steady state? Well, we don't really see any changes in temperature over time. We assume that T1 and T2, whatever they are, or T infinity, whatever they are, they're just numbers, okay? So we assume steady state for now. Is heat transfer happening radially? Or yes, we are going to assume, right, that this rod, however long it is uniform. And we're going to also assume that this rod length L is large enough that we can neglect the heat transfer that's happening to the environment off of the caps, right? So all of the heat transfer is happening off the curved surface, right, into the environment, and we can neglect the heat transfer that's happening, here out, okay? And if we do that, then we can reasonably assume that all the heat transfer in the system is occurring radially, okay? So it's going outwards, right, radially outwards. The problem is that we can't assume that there's no volumetric thermal energy generation because, of course, there's a Q dot right there. So can we even handle this sort of system at all? And the answer is yes. The only thing that we have to do is to remember carefully what, the thermal circuit foundation, the key idea behind the usage of thermal circuits, which is that we can take a system that satisfies all four assumptions and model it like a thermal circuit. And so this inner portion doesn't satisfy the four assumptions, but the cladding does, and the environment does. So why don't we just model this like it's a thermal circuit that's connected to this goofy Q dot, right? Why don't we model the cladding in the air as a thermal circuit and then just add in this goofy little Q dot on one of the sides of the system? And so what we can do is that we can then represent this as what I often refer to as a thermal circuit plus, right? Which is just a thermal circuit plus an element that has thermal energy generation, which we can't really model or think about using the standard assumptions for thermal circuits. So what would that look like in this case? Well, the first thing that we have to do is to say, okay, well, we know that this is not going to be a thermal circuit, so we're not going to touch this, right? We're not going to change this into a thermal resistance. We're just going to say, okay, well, this is just going to be Q dot. All right, this is just a ball with Q dot on it. But the cladding can be connected to this little object. And we can represent it, because it's made out of a solid, as a cylindrical conductive thermal resistance. And what is that cylindrical conductive thermal resistance? Well, all it is just as we had derived previously. It's the logarithm of the outer radius over the inner radius, so R2 over R1, divided by 2 pi times the thermal conductivity, which is K2, right? K2, and then L, right? So that length. So that's my conductive cylindrical thermal resistance. What about the air? Well, the air is just convective. So because it's convective, the expression for it doesn't change, right? Convective thermal resistances always have the same form, which is just 1 over HA. 1 over the heat transfer coefficient times the surface area over which the heat transfer takes place from the boundary of the object into the fluid. But what is this surface area, right? We're not told what the surface area is. And once again, assuming that this is one-dimensional heat transfer, that all of the heat transfer happens on this curved outer surface, then this area is just the surface area, the curved portion of the surface area of a cylinder. And what is that? Well, we had talked about it before. You just take the perimeter of the circle and you just project it, right? And so then this would be 2 pi, the radius, which is R2, times L. And so this is the thermal resistance for convection. All right, so this is for cylindrical conduction, and this is for convection. And so this is a pretty simple series thermal circuit. It's connected in series, right? Because remember that the direction that we care about is outwards. And so you can see that if we think of outwards as a single direction, the cladding and the air come in sequentially, right? The cladding isn't like split in half, and there's, half at this same radius and half that has different material properties at that same radius, or something like that, right? This is just a nice series circuit. So the only thing that's really new and tricky about what we're doing here is this Q dot, this little ball. So how do we find, for example, the Q that is going through this thermal circuit as, say, a function of the Q dot? So suppose that we know the Q dot. Suppose that we know all of the geometric properties of this little cylinder over here. How do we find the Q? Are they related, right? Because I am able to figure out everything that I want about the thermal circuit part of this system if I can find what this Q is. Okay, like if I didn't know what T2 was or one of these temperatures was, as long as I could find the Q and as long as I had information about the thermal resistances, I'm fine. Okay, so how do we relate the Q to the Q dot? Energy balancing, all right? So if I draw a little control volume, right, and I try to do energy balancing on this region of space, which I guess I could also just write it down over here, makes it easier, right? We know that all of the energy that is being generated inside of this little ball or cylinder, inside of this cylinder core, has to go outwards. Why? Because we know from energy balancing that if this system is in steady state, the thermal energy of the rod can't change over time, right? And we also know that because the system is in steady state, the only thing that is contributing, the only thing that can contribute to this outwards heat transfer, or outwards heat transfer rate, is an energy generation term. So skipping, the process of setting up the equation, what do we get? Just like before, I'm going to kind of assume that we know these things, all right? So I'm going to keep them, I'm going to say that this is our cylinder, I'm going to say this is our convection, and then just erase them and work with the base resistances. So how do I make this relationship happen? Well, I know that, E dot sys is equal to E dot in minus E dot out plus E dot gen. The thermal energy of the system, the rate of change of the thermal energy of the system is 0. And the energy coming in is 0, right? All of the energy is moving out, all right? There's no flow inwards, or at least we assume that to be the case. So this is 0 too. And so we're left with this, which says that E dot gen is equal to E dot out. And if this is the case, well, what is E dot gen? Well, this was a volume integral, right, of the volumetric thermal energy generation rate inside of this cylinder. But if we assume that this Q dot is uniform, that is, that it's the same everywhere inside of the cylinder, we can replace the integral with a multiplication, where this is just Q dot times the volume of this cylinder. And we can also replace this E dot out with the heat transfer rate out of the cylinder, which is just the Q that we're looking for. And so the relationship is pretty straightforward, right? It's just Q dot times the volume is equal to Q. But what is this volume? Important to remember, the volume that we're considering is specifically the volume of the cylinder core. It's not the volume of the whole thing. It's just of the little core where the heat transfer is occurring. Or pardon me, the heat generation is occurring. So what is the volume of a cylinder? Well, this time, all we do is we just take the cross-sectional area of the circle and then project it forwards, right? So this is just pi r1 squared times L. And this is equal to Q. And so now we've been able to figure out what Q is as a function of Q dot and these other geometric variables, okay? So now we have it. Now that we've got this, right? So I'm going to, let me write this over here so that it's a little bit more visible. I don't block it. There we go. Right, so now that we have this expression, what can we do with it? Well, we know the Q, and so all we have to do now is, who cares about what's going on over here? Is if you're trying to find a temperature at a boundary or something like that, you don't actually have to care about what's going on in this, heating cylinder, because all of the information about the thermal circuit has been pulled from this relationship. And so I could figure out, for example, what the temperature over here is or what the temperature over here is by doing a thermal circuit analysis and forgetting this ever existed. Okay? So, great. Now, before I finish up, there's one other thing that I wanted to mention, which is how do we find the temperature distribution inside of each portion of the cylinder? Like, what is that temperature distribution going to look like? And the answer might seem like it's kind of obvious because we already talked about this a little bit, but the Q dot is going to throw a wrench in things. Let me show you how it does it. So let's start with the cladding. Okay? And I'm going to be relatively quick on this one because we've already kind of seen what the temperature distribution looks like, but bear with me. In the cladding, all four assumptions that we use to construct thermal circuits are true. And those same four assumptions led us to express in radial, cylindrical radial coordinates, that the heat equation simplifies into something that looks like this. Right? So this is what we had kind of found when we applied those four assumptions for a cylindrical system where the heat transfer is happening only radially. The k, of course, doesn't matter. It doesn't show up because we can always divide by k on both sides. Now, for example, if we didn't know a temperature, but we only knew a heat flux that was happening on a boundary, then the k would show up, but not as a result of the integration process over here, but it would show up as like part of the boundary condition, right? Like maybe the heat flux is a function of k, and then there it would get plugged into the equation, but it never shows up in the actual differential equation we need to solve. So we have this expression. We already saw what happened when we integrated this, right? Which is that eventually we get to the point where the solution, the general solution to this, is C1 times the logarithm of R plus C2. Now we don't have to get too deep into trying to figure out what C1 and C2 are. We already found expressions for them in previous lectures. The important thing to know is that, do they matter? Are they not zero? Is there any gotcha? And from this perspective, there isn't, right? Because C1 and C2 are determined based off of the boundary conditions that we can establish for the cladding. Okay, so we would say something like, well, the temperature at R1 has to be T1, and the temperature at R2 has to be equal to T2. And so in that scenario, we don't actually run into any problems associated with, evaluating, temperatures at R equals 0, or evaluating logarithms at R equals 0, and then having things blow up to infinity, right? So this expression works out. The constants are just determined based on the values of T1 and T2, or on the values of the heat fluxes and heat transfer rates at the boundaries, right? But the point is, we've already seen this before. Nothing too interesting here. In the rod, however, something funny happens. And the thing about the rod is that the q dot term in the heat equation is not zero. And so as a result, the expression that we get, the ordinary differential equation that we find, is actually not the same. Why? Because, right, what we will wind up obtaining is just the same kind of left-hand side, but now there's a q dot, right? So now it's 1 over r, d over dr, kr, dt dr, right? But this is plus q dot is equal to 0, okay? Now the k comes out over here, but unlike what happened before, now we can't just get rid of the k by dividing on both sides. Because sure, this is still 0, but now you get a q dot over k. So the k shows up in the solution to this equation now, which is a very interesting little fact. So what we essentially have is what in the language of ordinary differential equations is called an inhomogeneous, I don't know how to pronounce it, doesn't matter, inhomogeneous version of this equation, where now this is just minus q dot, okay? And the beauty of the fact that this is the same ordinary differential equation, a nice linear ordinary differential equation, but which has this extra q dot term in, is that the answer to this ordinary differential equation is going to be the same general answer plus an extra term, all right? So from math, right, so it doesn't have to do with physics, just mathematically, the temperature in the core is going to look like something that's like C1 logarithm of R plus C2 plus something else. That's what we're going to wind up getting. So we have to try to figure out what the something else is. So what is the something else? Something else. So take the k, move it down over here, q over k. You have 1 over r. Take the r, move it over to the right. All right, so we have this. Now all we have to do is just integrate this whole thing as a function of r. And so what we obtain is that r dt dr is equal to minus q dot r squared over 2k. And so now that we have this, what can we do with it? Well, we can always take this r squared, divide by r, and then obtain this, and then just integrate that again. All right? So we just get an r squared back, but now this 2 gets replaced with a 4. And so just to be completely clear, right, throughout this entire process, I would be getting integration constants that would show up, and those would matter too. I've been skipping that step because the thing that we get from the integration constants is just this, right? It's the thing that we saw all over again. The new term, the only thing that we really care about deriving is this, okay? And so the extra term is now a minus q dot r squared over 4k. So this is the general expression for what the temperature profile looks like inside of a rod that has uniform thermal energy generation inside of it. And now notice that the K shows up, right? Is this it? Well, remember the logarithmic term. If we try to evaluate this thing at r equals 0, the temperature explodes. And the way that we got around that was by saying that C1 had to be equal to 0. And there's no difference here, okay? Here, we have to say that C1 is equal to 0 in order to avoid that temperature blowup. And so what we're left with is just some constant C2 minus q dot r squared over 4k. I guess I should write it over here to make it a bit clearer that this is a subtraction. Q dot r squared over 4k. And why is this meaningful? It's because it changes fundamentally the equation that tells us how the temperature actually changes with space, right? So in the cladding, the change is logarithmic, right? It decreases logarithmically, we assuming that, the heat transfer is happening outwards, which it has to be because of the q dot. So we assume that as you move outwards in R, in the cladding, the temperature decreases logarithmically. Here, the temperature is not decreasing logarithmically at all, it's decreasing parabolically, right? It's decreasing with the square of R. And so if you actually took a look at what the temperature profile of this whole cylinder looked like, what you would wind up obtaining is that, let's say that this is R and this is T, you'd find that out here, the temperature decay is logarithmic. So in the cladding, but once you hit the actual inner core, this thing becomes parabolic. Now, in terms of the sketching, why does it have to be decaying? It has to be decaying because of the fact that, well, the heat transfer is occurring outwards, right? If it's occurring outwards, that means that the temperature has to decrease from inside to outside in order for the standard assumption of how heat transfer works to work. Then, why isn't it, say, concave this way? So why is it kind of curved in this direction? So I get this question a lot from students, which is, why does the curve go down this way? And the answer is just that, well, that's what the logarithm is going to look like whenever you do these sorts of problems. But also you can imagine that as the cylinder becomes larger and larger and larger, you expect the heat transfer that's happening through it, or at least the temperature distribution, you expect the temperature distribution to eventually kind of at least approximately smooth out. And if this thing curves down this way, then that just means that the temperature decreases steeper and steeper, right? What you want is for the temperature decrease to be gentler and gentler as R increases. So that's a way to think about it. Over here, we know this is a parabola, but what's the shape? We know it has to match over here, right? And so what we could do is, if we know what Q dot is, if we know what T1 is, we can always, just as before, say that, well, like T at R1 has to be equal to T1, which has to be equal to C2 minus Q dot R squared over 4K. Right? And then we can just solve this directly to find what C2 is as a function of T1. And so mathematically, this is how we would get the expression. Conceptually, what will happen is that the temperature distribution inside of this thing will actually look a little bit like this. It's a bad drawing, where the section inside of the core is a parabola, flip parabola. So why does it look like it's kind of curving downwards? The negative term is responsible for that. But also notice that the point at which its derivative is exactly equal to 0 is right here in the center at r equals 0. That's, once again, a mathematical consequence of the fact that there's no linear term over here, right? If you take this derivative, this goes away. You get something that's just linearly proportional to r at r equals 0. That stuff goes away. But fundamentally, there's another key physical reason, which is that there is no heat transfer inwards or outwards exactly at the core, right? Because at the core, the notion, like inside at the very center, at the origin of the cylinder, there is no longer a consistent definition of inwards or outwards. And so as a result, the only way that this kind of approach works is if we say, or observe, I guess, if you trust the math, that the heat transfer rate and the heat fluxes and the temperature gradients at the very center of the cylinder have to be exactly 0. Does that make it seem like, the heat transfer rate everywhere inside of the cylinder is equal to 0? No, because of the fact that we have the q dot, which means that the heat fluxes and the heat transfer rates aren't conserved as a function of r. So this is only happening because of the fact that we have the q dot. And so this is a perfectly consistent and nice description of what the temperature profile looks like inside of the system. And we already figured out how we can calculate the C2 for the temperature in the core and how we can calculate the constants for the temperature profile inside of the cladding as well. And so we can, if we wanted to, write a precise version of what this graph looks like. And so this is everything that helps us to understand not just how we handle cylindrical systems, all of the intricacies, of how the geometry factors in, but also it helps us understand what happens when I have an element with a thermal energy generation inside of it. And the point is that it's not really an obstacle, right? All that you do is that you just model this thing as a thermal circuit plus, as something that is a thermal circuit with some thermal energy generation thing attached to it. And so this will be a very fruitful way of expanding or extending the logic that we use for modeling systems that have, the 4 key assumptions we always use, and how we can extend that to systems where maybe those 4 assumptions work for some chunks of it, but not all of the chunks of it.